We are going to start out with organic chemistry first, okay? We're going to do organic chemistry today, a topic of organic chemistry in this demo class. Organic chemistry. And the topic we are going to do today is, first we are going to do isomerism, right? Isomerism. And then we'll touch upon alkanes a bit. Okay, the two objectives of our today's class. All right, so let's get started. All right, so isomerism. Okay, from your O levels, we know that isomers are compounds having the same molecular formula. And different structural formula. Okay, so for instance, if this was a compound, okay, this is propane. Actually, I'll use butane, CH2, CH3. Okay, this is butane, and an isomer of butane will have a similar molecular formula but of a different structural formula, so it can be branched at one point. Okay, both these compounds have the same molecular formula, C4H10, but their structural formulae are different. Okay, this is a straight chain compound and that's a branched. This is, I'm assuming that you already know from O levels. Okay, this is branched. This was the only type that we did in O levels, right? But in AS, isomerism is a bit more extensive. Okay, and this isn't the only type of isomerism that exists in compounds, but there are many more. Let's do them one by one. Okay, so isomers. Isomers can be chain isomers. Okay, the first type of isomers is the chain isomers, which we just saw. Second type is known as positional isomers. Third type is known as functional group isomers. Instead, I'll classify them even better. Wait, I'll classify them even better. Actually, isomers are broadly classified into two main categories. Okay, two main categories. The first one is known as structural isomers, and the second one is known as stereoisomers. Then underneath the structural isomers, we have the chain isomers, we've got the positional isomers, and the functional group isomers. Whereas underneath the stereoisomers, we have two types. Okay, the first type is known as geometrical isomers, which is also called the cis-trans isomers. And the second type is known as optical isomers. All right, you should know how to define each one of them. First of all, let's define what structural isomers mean, because this definition is very commonly asked in the past papers. The examiner just asked you to define what structural isomers mean. So structural isomers is, the definition is pretty simple. It's more or less the same as the one you've been doing since O levels. Okay, structural isomers are compounds having the same molecular formula, and different structural formula, and that's it. Different structural formula, and these are the only 2 points you need for defining structural isomers. Okay, this is the definition of structural isomers. And stereoisomers. Stereoisomers are very interesting type. Okay, these isomers are actually have the same molecular formula, and they also have the same structural formula. Okay, so if the structural formula and the molecular formula both are the same, then what's the difference? Okay, here's the difference, but they have a different arrangement of atoms in space. Basically, if they are oriented in a three-dimensional space, if we keep them in a three-dimensional space, so they'll point towards different directions. They'll be oriented in different directions. Okay, so their 3D shape, or in the 3D space, they'll have a different arrangement. That's why they are called stereoisomers. Okay, now let's look at each type one by one. Okay, first of all, the chain. Okay, before I proceed, any questions so far in the two categories of isomers? Was there any questions?
No.
All right, cool. Now let's look at the structural isomers one by one in great detail. And this is a very important part of your organic chemistry, because most of the time questions do come on this part of the organic chemistry. Okay, although this is a very basic level, but it is a very important one, high yield with respect to your exams. Okay, now chain isomers. These are the same, exactly the same as the ones you've been doing since O levels. Okay, they have their chains, their carbon skeleton is different. Okay, so they can either be straight chain or branched. Straight chain, or they can be branched. Okay, they can even be cyclic. All right, but I won't discuss the cyclic for now. Okay, just leave cyclic for a bit because it might confuse you. There's the straight chain and the branch are the two easier categories first. Okay, so they can be straight chain or branch, and I gave you the example up here, somewhere over here. Maybe I removed it. Anyways, the butane and the 2-methyl-pro, okay, it's right over here. Yeah, these are the two chain isomers. Okay, the carbon chain is different. Okay, in both of them. If you okay, we'll even do the naming. Okay, in detail. For now, I'm just assuming that you know the O levels naming. The 4-carbon compound is known as butane. Okay, and this compound is known as 2-methyl-propane. And you don't need to know, you don't need to worry about the naming for a bit, because we'll have a separate class on the nomenclature. Okay, for now, just know that this is the name of this compound. Just know their carbon skeletons are different. Okay, that's why they are chain isomers, or they are structural isomers, but their carbon skeletons are different. So now, if the examiner asks you to define what chain isomers are, so how to define them, and sometimes the definition is for 2 to 3 marks. Okay, so if the question comes to define what chain isomers are, so basically you can define the chain isomers. First of all, you need to identify, is it a structural or a stereoisomer? It's a structural isomer. Okay, so the definition, this basic definition of structural isomer must come in the definition of each of the 3. Okay, it must come in the definition of each of the 3. Now, this chain isomers, so first you need to define it by saying that these are compounds having the same molecular formula. And different structural formula. Okay, this basic definition will come. Different structural formula. And then you need to specify how is the structural formula different in this case. The structural formula is different. How? That is, they have the different carbon skeleton. That is, they have different carbon skeleton. All right, so this is a complete definition of chain isomers, and I gave you the examples. Let's do one more example. Okay, for instance, This is a compound CH3, CH2, 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 CH3. All right, and then if I were to talk about its isomer, its molecular formula is C5H12. Okay, this is pentane, and the compound, the isomer can be CH3, the C, another C, and then a CH3 attached maybe over here. Okay, this is one possible isomer. Okay, we can have more than one isomers. Okay, we could have this chain. We could have another branch on the same carbon atom over here. Okay, we could have another branch like this. And CH3, 1, 2, 3, 4, 5. Okay, both these compounds are structural chain isomers of this pentane, and they have the same molecular formula of C5H12. Okay, but their structural formulae are different. All right, so this is how you define what chain isomers really mean. Okay, is it clear? Any question so far in chain isomers? There? What is carbon skeleton? Okay, carbon skeleton is actually this backbone of carbon atoms. Okay, this backbone. Okay, this connectivity of carbon atoms, the carbons which are attached, this carbon atoms. This chain is known as the carbon skeleton. So if I were to change this chain by branching it, by taking the carbon atom from the corner and attaching it somewhere in the middle, it would form a different carbon skeleton. Okay, this is known as a different carbon skeleton. Or if I were to take a third carbon atom and attach it over here again, then I would have another possible carbon skeleton. These carbon atoms connected to by covalent bonds form a carbon skeleton. Clear?
Yes.
All right. Now, is there any other question you want to ask related to chain isomers, or should I move ahead?
No, sir.
All right. So just remember that this is the complete definition of a chain isomer. Okay, this is what you need to write in your exam. Now, coming to positional isomers. Again, this is an example of structural isomers. So the definition of positional isomers is also going to be defined in a similar pattern. But the thing is, you need to first define the structural isomers as well in here, because the marking schemes, almost all the marking scheme have 1 mark or 2 mark for defining structural isomers before defining positional isomers, because this positional isomer is a type of structural isomers. Okay, so their compounds having the same molecular formula, different structural formula, and how are the structural formulas different? Now let's look at them. Positional, right? Positional, as the name suggests, positional means that the position of the functional group is different in each compound. Now, let me take an example. For example, I have propanol, CH3, CH2, CH3, 2 OH, a 3-carbon alcohol. Okay, this is propanol, and this OH group over here is the functional group. I hope you know what functional group means. Okay, from your O-levels knowledge, functional group is actually the reactive site of the organic compound, or that site or that groups of atoms, the group of atoms which give its characteristic chemical properties. The group of atoms which give this organic compound its own characteristic chemical properties is known as a functional group. Chemical properties, responsible for the chemical properties. Okay, but don't worry, in AS you are not asked to define what functional group really means. Okay, because it's assumed that you know it already from your O-levels. Anyway, so functional group is the reactive site of a compound. In this case, the functional group is the OH atom, the OH group. Now, positional isomers. If I were to name this compound, it's a 3-carbon alcohol, right? 3 carbons means pro. 3 carbon means pro, and this OH group is on the first carbon. It's on the first carbon atom. So the name becomes propan 1-ol. Okay, the name of this compound is propan 1-ol. 3 carbons imply pro, and 1 implies the position of the functional group, and all implies that it's an alcohol. Now, if I were to change the position of this functional group, the functional group is the same. Okay, the functional group is not changing. It's just that its position is changing. And if I were to place it on the second carbon, okay, I take the functional group from the terminal carbon and I attach it on the second carbon over here. This is the compound that I get. Okay, and this compound, the name of this compound now becomes, if I were to name this carbon skeleton, is going to be 1, 2, 3. It's on the second carbon. Okay, we have the OH group on the second carbon, so the name becomes propan-2-ol. Propan-2-ol. Okay, propan-2-ol. Why 2? Because now the OH group is on the second carbon. These two compounds, the propan-1-ol and propan-2-ol, propan-1-ol and propan-2-ol, these two compounds are examples of functional group isomers. Not functional group isomers. I'm sorry, it's positional isomers. Positional isomers. So compounds having the same molecular formula, their molecular formulas are the same, C3H3578. Okay, you can write it as H7OH. Okay, C3H7OH. The molecular formulas are the same, but their structural formulas are different. How are their structural formulas different? Because they have a different position of functional groups. Okay, positional isomers. So if you were to define it, what positional isomers are, they're compounds having the same molecular formula, different structural formula. That is, they have different positions of the same functional group. Remember, it's the same functional group. The functional group is not changing, of the same functional group. Why am I stressing on the word same? Because there is another type of isomerism in which the functional group changes, and that's known as functional group isomerism. Okay, the same functional group is present, but its positions are different. Now, what about the functional group isomerism? I just told you. Okay, again, the first 2 points are going to stay the same. Same molecular formula. Okay, it has the same molecular formula, different structural formula. But how is the structural formula different? It has different functional groups. Now, in this case, guys, the functional group is changing. Okay, the functional groups are changing, and I'll give you examples of these as well. Okay, now remember, in our syllabus there are a few cases, actually 3 types of functional group isomers, 3 pairs of functional groups isomers actually. Right, the first pair is aldehydes and ketones. I'll tell you what they are, aldehydes and ketones. The second pair is acids and carboxylic acids and esters. Okay, this is also something you might have done in O-levels. Carboxylic acids and esters are isomers. Which isomers? Functional group isomers and esters. The third type is alcohols and ethers. Now I'll explain one by one what each of them mean. Now, taking the first point, aldehydes and ketones. Okay, first of all, remember, aldehydes are compounds having the functional group C double bond OH attached to it. Okay, these are compounds. This is the functional group present in aldehydes. Okay, there is a whole detailed chapter on aldehydes in the upcoming lectures as well that we are going to do in the same organic chemistry. Okay, aldehydes and ketones are compounds having the C double bond O functional group. So this is R and R prime, and this is R. Okay, so these are the 2 general ways of writing an aldehyde and a ketone. Okay, aldehyde. Okay, what does this R represent? This R is actually a hydrocarbon chain. Okay, hydrocarbon chain, or a carbon skeleton basically attached with hydrogens. Now let's take an example of aldehydes and ketones. Okay, I'm taking a 3-carbon aldehyde. A 3-carbon aldehyde is known as propanal. Okay, Al in the end, not Ol, not alcohol, it's Al. Okay, just remember this difference between aldehydes and alcohols. Okay, 3 carbon aldehyde, so it's gonna look something like this: CH3, CH2, C double bond O attached to a hydrogen. All right, this is a 3 carbon aldehyde. Now it's called propanal, and if I were to write down its structural formula, oh sorry, its molecular formula, so it's gonna be C3H56O. C3H6O. Now let's take a 3 carbon ketone. A 3 carbon ketone is known as propanone. Okay, and this is actually the first ketone of the ketone series, and this is how it looks like: CH3, C double bond O, CH3. Remember that in ketones there must be a hydrocarbon chain on both the sides of this carbonyl group. This C double bond O group is known as a carbonyl group. Okay, this group is known as a carbonyl group. Since it's present in both aldehydes and ketones, so therefore aldehydes and ketones are also collectively called carbonyl compounds. Carbonyl compounds. We are going to look at this in great detail in that lecture of aldehydes and ketones that's going to come later on. But anyways, this is what aldehydes and ketones look like. If I were to write down its molecular formula, the molecular formula of this ketone, of this propanone, is C3H6O. All right, C3H6O, C3H6O. They have the same molecular formula and they have different functional groups. Okay, in aldehydes, I told you this entire thing is considered a functional group. It's not just the carbonyl compound that's considered the functional group. And in ketones, it's just a carbonyl compound that's the functional group in here. Okay, that is surrounded by, that has CH3 groups on both the sides. Okay, since they have different functional groups, but they have the same molecular formulae, therefore these are examples of functional group isomers. All right, any question in aldehydes and ketones? Was there?
Sir, in the first aldehyde was a hydrogen in the carbonyl.
Yeah, we have a hydrogen atom over here right next to the carbonyl group in an aldehyde. Whereas in ketones, we have carbon atoms on both the sides. Is this what you are asking? We have a hydrogen atom, a terminal hydrogen. This is called a terminal hydrogen.
But in the other, there is not present a hydrogen
Yes,
atom.
it's not present, exactly. Because in here, in ketone, it's the condition that the carbonyl group must have 2 carbon atoms on both the sides. Whereas in aldehyde, it's the condition that it must have a terminal carbon. Okay, if this terminal carbon is replaced by a carbon atom, it becomes a ketone. And if this carbon atom is replaced by a hydrogen atom, it becomes an aldehyde. Okay, so remember, this is the basic distinction between them, that in aldehydes, we even have a hydrogen in the functional group, whereas in ketones, we only have 2 carbon atoms on both the sides. We don't have any hydrogen, any terminal hydrogen attached to it. All right?
Okay.
Okay, any other question over here? Should I move on?
Yes.
All right, so this was the first case of functional group isomers, carbonyl compounds. Now coming to the second example of functional group isomers is carboxylic acids and esters. And this is something you've already done in O-levels. Carboxylic acids, you are familiar with what the carboxylic acids look like, and you are also familiar with esters. Okay, carboxylic acids are compound having the COOH functional group, and esters are compounds having the C double bond O with an O attached functional group. Okay, the ester functional group and the carboxylic acid functional group. This is the functional group present in esters. This is the functional group present in carboxylic acids. Okay, in esters, on both the sides, we can have carbon atoms or hydrogen atoms. In carboxylic acids, we can have a carbon atom or a hydrogen atom over here. Okay. Now, let's take examples. Let's take a 3 carbon acid and a 3 carbon ester. All right, 3 carbon acid. It's called propanoic acid. Propanoic acid. And 3 carbon ester that I'm going to make is going to look something like this: CH3 C double bond OO with a CH3 attached to it. All right, how to name esters? Well, this the side which comes after the oxygen atom, it's called the alkyl side, and the side which comes before the oxygen atoms is called the alkanoate side. Okay, alkanoate is the general way of naming esters. Okay, this alkyl and alkanoate, this ALK can be replaced by meth, eth, pro, but. Okay, depending on the number of carbon atoms which are present. Now, for example, over here we have only one carbon atom, so this will become methyl, and we have two carbon atoms on the left hand side, right? The carbonyl carbon and this carbon atom. So two carbon atoms is known as eth, right? The eth means two carbon atoms. So methyl ethanoate. This is the ester that we have over here, and this carboxylic acid that we have on the left hand side is CH3 CH2 COOH. This is called propanoic acid. Now, if I were to write down its molecular formula of both these compounds, the molecular formula of this carboxylic acid will become C3H6O2. The molecular formula of this compound will become C3H6O2 still. So, are the molecular formulas the same? Yes, they
Yes.
are. And their functional groups are different, right? We have a OCOH group and an ester group. So since their functional groups are different, their molecular formulas are the same. So these are also examples of functional group isomers. Clear?
Yes, sir.
And general way of writing the name of esters is alkanoate. We'll practice the naming too, so don't worry about that, right? And now the third type is alcohol and ethers. Our functional group isomers, alcohols and the corresponding ethers. Okay, alcohols are compounds having the same general formula of ROH, whereas ethers are compounds having the general formula of ROR. All right. So now in ethers, it's just this middle oxygen, that's the functional group, and in alcohols, it's the OH group, that's the functional group. Okay. So now if I were to take examples, okay, let's take a 2-carbon alcohol and a 2-carbon ether. So the 2-carbon alcohol is going to be CH3 CH2OH, right? And 2-carbon ether is going to be CH3OCH3. Now, both these compounds, if their molecular formula is written, it's going to be C2H6O and C2H6O. Their molecular formulas are the same, and their functional groups are different. What is an ether? Ether is a compound having this ROR configuration. Okay, it's oxygen that's present in here. That's the functional group for an ether. This is new for you, I know. It was not in O levels. Okay, this is the functional group of ethers. So compounds having this O as the functional group is known as an ether, and it's generally it's not that frequently tested though. The ethers are not that frequently tested, but in the MCQs they do show up. Okay, they do show up. So it's better to know. This is how the ether looks like. This is what the ether is. Okay, the oxygen is the functional group, and both the sides must have a carbon skeleton in ethers. Do you get it?
Yes.
Okay, and if one of the two sides is replaced by a hydrogen, okay, it's just like aldehydes and ketones. Remember, in aldehydes we had a terminal hydrogen. Over here as well, in alcohols we have a terminal hydrogen, and if both the sides are replaced by a carbon atom, by carbon atoms, then it becomes ether. Okay, so you could consider this as similar to ketones, consider ethers to be similar to ketones, and consider alcohols just to remember to be similar to aldehydes. Okay. So it's just the terminal
Okay.
hydrogen that differs in both the cases again. All right, and well, the naming of ether is not in the syllabus though, but I'll still name it. It's called a dimethyl ether. Dimethyl ether. And this is what you already know from O-levels. It's a 2-carbon alcohol. It's called ethanol. There's another way of naming it too, but let's not go into that for a while. Okay, so these are the 3 cases of functional group isomers. Okay, aldehydes and ketones, carboxylic acids and esters, alcohols and ethers. Okay, and these are the 3 cases that are generally tested in the past papers for functional group isomers. Okay, because these are the ones in our syllabus. So functional group isomer is done, positional isomers is done, and chain isomers is done. Any questions so far in these 3 isomers? Was there any question?
No, sir.
All right, so let's go on to stereoisomers then. Okay, stereoisomers. All right, whenever you are asked to define what stereoisomers are, okay, basically generally in the past papers, a definition of stereoisomers is asked, okay, rather than the asking the definition of optical isomers or geometrical isomers, the examiner tends to ask the definition of stereoisomers. Okay, so stereoisomers. This is a definition of stereoisomers. They have the same molecular formula, same structural formula. Okay, this is the distinction between structural isomers and stereoisomers. And stereoisomers are completely new for you guys because stereoisomers is something you've not done in O-levels. Okay, you've only done the chain isomers of the structural isomers in O-levels. Stereoisomers are compounds having the same molecular formula, the same structural formula, and different arrangement of atoms in space. Okay. Now, the 2 isomers, the 2 types are geometrical isomers and optical isomers. And we are going to define each of them one by one. Okay, let's first look at geometrical isomers. Which are also known as cis, trans isomers. Okay, cis and trans, these are actually the 2 types of isomers which are present. Okay, cis configuration, this is one configuration, the cis configuration, and this is the other configuration known as the trans configuration. Okay, first of all, the conditions in which the cis trans isomerism is possible. Okay, first of all, let me tell you something. Cis trans isomerism is possible in compounds having a pi bond. Okay, now, do you know what a pi bond is? You don't know, right? Let's do pi bond first. Basically, the covalent bonds which are made, covalent bonds. They are made by orbital overlap. Okay, they are made by orbital overlap. Okay, you might not know what orbital is. Okay, for now, just assume. I'll just give you something to begin with. All right, pi bond is basically the second bond which is formed after the sigma bond. Okay, first of all, we have 2 types of covalent bonds. Okay, we have a sigma bond and a pi bond. Okay, these are the 2 types of covalent bonds. Okay, sigma bond. What is a sigma bond? Sigma bond is basically a bond which is present in basically all single bonds are sigma bonds. All single bonds are sigma bonds. And double bonds contain pi bond and sigma bond both. Double bonds contain sigma and pi bonds. Now I'll tell you what both of them means. So now, for example, if I have this compound, this is an alkene. You know what alkene is, right? From your O-level knowledge. This is an alkene, this is a 4-carbon alkene, okay, which is known as butene. And to be more specific, this double bond is the functional group, right? if I were to name this carbon skeleton, it's going to be 1, 2, 3, 4. This double bond comes right after the second carbon, right? So if it's after the second carbon, so the name of this compound is going to be butene. Now, in this compound, all the single bonds which are there, they are known as sigma bonds. Okay, for now, just remember that all the single bonds are the sigma bonds. And this pi bond, pi bond formation, how did the pi bond formation occur? First, a sigma bond was made. Okay, first a sigma bond was made. Okay, first the single bond was made, which was the sigma bond. And then secondly, the second bond which was made was the pi bond. Okay, so a double bond, a carbon-carbon double bond is actually a combination of sigma and pi bonds. And in fact, all the bonds which are made after this single bond are all pi bonds. Okay, so for example, if I talk about a molecule of nitrogen gas contains a nitrogen-nitrogen triple bond. In nitrogen-nitrogen triple bond, first a sigma bond was made. Okay, this was the first bond which was made, and then the next two bonds which are made are the pi bonds. Two pi bonds were made. So this is what sigma and pi means. Okay, sigma is basically a single bond. All the single bonds are known as sigma bonds, and this is the pi bond, which is made after the sigma bond. And by the way, the sigma bonds are stronger than the pi bonds. Sigma bonds are stronger than the pi bonds. Sigma bonds are stronger than pi bonds. Okay, remember, just focus on my wording. I said sigma bonds are stronger than pi bonds. I didn't say that single bonds are stronger than double bonds. Okay, I didn't say single bonds are stronger than double bonds, because double bond is not actually a pi bond alone, but it's rather a combination of both a sigma and a pi bond. So double bonds are stronger than single bonds, but a sigma bond is stronger than this red pi bond. Okay, this is something you need to learn. Second property of a pi bond is this pi bond. What it does is this pi bond actually it locks rotation about the pi bond axis. Actually, the sigma bond axis. Sorry, the sigma bond axis. Now, for example, if I draw an imaginary axis right over here that cuts this entire molecule into two equal halves, so this pi bond, what it does is it locks rotation. What do we mean by locking rotation? It locks rotation. Locking rotation means that this carbon atom up here, the CH3 group, this can no longer now come in the position of this hydrogen atom, and this hydrogen atom cannot go in the position of that CH3 group. This is because of this pi bond over here. So you could just think of this pi bond as a lock on top of this carbon-carbon single bond. Okay, so this is actually a type of lock which holds this molecule, which makes it very rigid, which makes the carbon-carbon double bond rigid and prevents these molecules from rotating, and prevents these molecules from moving from above to lower side and from lower side to the upper side. Okay, so it actually prevents that happening. All right. Basically, what this locking rotation means, that just remember it for now, that this pi bond, what it okay, I'll explain it. Think of it this way. I have two compounds. Okay, both are double bonds. All right, this is one compound, and now I have another compound. In this compound, what has happened is that this CH3 is at the same position, the hydrogen is at the same position. Okay, but this CH3 and the hydrogens, they have changed their position. CH3 and a hydrogen. Now, I was telling you that it's not possible for this same compound, to change from this configuration to that configuration in presence of a pi bond. Okay, if you look at it carefully, what has happened is actually this methyl group has rotated. It has moved on and replaced this hydrogen atom, and this hydrogen atom has moved up and replaced that carbon atom. Okay, these two compounds are actually two different compounds. Okay, these are two different isomers of each other. These are two different isomers of each other, and I'll tell you why they are called isomers in a bit. But this is what rotation means. Locking rotation. Can it rotate? Yes. In case of sigma bonds, it can. Now wait, let me. In case of sigma bond, now for example, if I have this compound over here, all right, there is no pi bond present in between the carbon-carbon bonds. Okay, and let's replace these hydrogens too. Okay, let's replace them by some other groups, methyl groups, for example. Now this compound, it's possible for this. These bonds are actually now free to move. Okay, because now sigma pi lock is not here. The pi bond lock is not present in here. Okay, so it's possible for this compound to come in this configuration as well easily without the need of using any more energy. Okay, it's possible for the same compound to come in this configuration, and so in this case, these two compounds are not considered two different isomers, but these two compounds are considered the same structure, the same compound. This is the same compound which has rotated, okay, in which the methyl groups have rotated. Okay, and it's possible because there is just a sigma bond and no pi bond lock is present over here. Just think of the pi bond as a lock. Okay, if the pi bond is present over here, then this rotation is not possible. Okay, if you want to rotate this compound, okay, if you want to rotate this compound, it would only be possible if you would break the pi bond, okay, by providing some energy. If you break the pi bond, then only the rotation will be possible, and then again if the pi bond is made, then again it will stay in that configuration and will not be able to move ahead. So consider the pi bond as a lock. Pi bond locks rotation. Do you get this pi bond locking rotation stuff? Because this is a very important property for cis-trans isomerism. This is the base of cis-trans isomerism. This is the reason why
Yes.
it can show cis-trans isomerism. All right. Now,
Sir, what effect this has on the properties of the compound, the rotation?
I'll tell you just a bit. Basically, first let me tell you what these isomers are called. Come on. All right. Now, this compound, okay, this was the first condition of cis-trans isomerism, that pi bond must be present in the compound. Pi bond must be present. And there is one more condition that must be satisfied for cis-trans isomerism to be observable. And the second condition is that the double bonded carbon atom, this double bonded carbon atom, both the double bonded carbon atoms, they must directly be attached to two different atoms or groups of atoms. Now, in this case, we have two different groups of atoms attached to the same carbon atom. Okay, this carbon atom over here has a hydrogen and a methyl group. Both hydrogen and methyl groups are different, right? So they're different, atoms or groups of atoms are attached to the same compound. And over here in this double bond as well, these two atoms which are attached, they are also different. Okay, so in this case, when both the atoms which are attached are different, only in this is the second condition when cis-trans isomerism is which is needed to show cis-trans isomerism, that the double bonded carbon atoms, double bonded carbon atoms must be directly bonded to two different atoms or groups of atoms. Now, what is the compound that cannot show cis-trans isomerism? Okay, although it has a double bond, but both the carbon atoms has two hydrogen atoms directly bonded to it. So now these two compounds are the same. These two atoms are the same actually. Okay, these two atoms are the same. So this compound, although this carbon atom would have two different atoms or groups of atoms attached to it, but since one of the carbon atoms is not bonded to two different groups of atoms, this cannot show cis-trans isomerism. Now, were the two conditions of showing cis-trans isomerism. Now I'll tell you how to identify a cis isomer and a trans isomer. Okay, what's a general way of representing a cis isomer and a trans isomer? Okay, now this is a carbon-carbon double bond. It has two different groups of atoms attached to it. Okay, now if the same group, focus on my words, this is the sigma bond axis. If the same group, for example, this R is one group, if the same identical group is attached on the same side of the sigma bond axis, okay, if it is attached on the same side of the sigma bond axis, such a compound is called a cis isomer. Repeat, if the same group of atom is attached on the same side, okay, regardless of the other side, we don't matter, it doesn't matter what atoms are present on the other side. Okay, it can be the same groups or can be different groups. For example, hydrogen and a CH3 are attached. Okay, let's not take a CH3 over here, let's take a bromine atom over here. Okay, for example, these are two different atoms attached on the other side. Okay, but these atoms, we're going to look at the same groups or same atoms, and since these two atoms are the same, okay, so I was saying that cis isomer is an isomer in which the same groups of atoms are attached on the same side of this green axis, of this sigma bond axis. This is called a sigma bond axis. Okay, so or you don't even need to name this axis. All you need to do is you just need to say that when the same groups are present either above the carbon-carbon double bonds or below the plane of the carbon-carbon double bonds. Okay, it can be below the planes of the carbon-carbon double bond. Such compounds are called cis compounds. Okay, these are cis compounds. And now, what is a trans isomer? A trans isomer is basically a compound that has the same groups of atoms attached across the double bond. Okay, now these are the same groups of atoms. Okay, R and R are the same groups of atoms, but they are present across this double bond, making a chair-like configuration. Okay, if you look at it, this resembles a chair. Resembles a chair. Okay, this is the base of the chair. This is the base of the chair. This is the back, and this is the foot. Okay, chair-like configuration. This is called a trans configuration. Okay, the remainder of the two sides can be any atoms. Okay, doesn't matter, but the same groups must be across the double bond. And if you have the same groups on the same side of the double bond, they form a table-like configuration. Okay, a table-like configuration. This is called cis configuration. That's called a trans configuration. Cis or crisscross. No, not crisscross. It's called cis. It's just cis. Okay, cis. I'm not sure about the crisscross. I've never heard about crisscross, but I've heard about cis only. Okay, so now let's do a few examples of cis trans. Okay, now for example, in this case, CH3 groups are attached on the same side, and hydrogen and a bromine atom are attached on the opposite side. Okay, so now if you look at the same groups of atoms which are attached, over here, in this case it forms a cis isomer. Okay, and if I were to form a trans isomer of the same compound, so how to form a trans isomer? Just place the same groups of atoms across the double bond. This is how a trans isomer looks like. Oh, actually, wait. This is a bromine atom. Okay, so this is a trans isomer. This is a cis isomer. Okay, the same group is across the double bond. Same group is on the same side of the double bond. This is a trans isomer, and this is the cis isomer. Cis trans. This is how you identify cis trans isomers. Okay, now if I were to write down their molecular formulas, how to write down their molecular formulas? Okay, let's write them down. Okay, this is a CH3 group over here. This is a carbon atom. Carbon has a bromine atom, so bromine is a branch, so you write it in brackets, and a double bond is there. Okay, and then you have a carbon atom which is attached to a hydrogen, and then you have a CH3 group over here, right? This is the structural formula of this compound, and if I were to write down the structural formula of the trans isomer, it's also going to be the same. It's going to be CH3, carbon, the bromine, double bonded to a carbon, which has a hydrogen and a CH3. Okay, the structural formulas are the same, and their molecular formulas are also the same. They have 4 carbon atoms, C4, the hydrogen atoms 3, 6, 7 hydrogen atoms, and a bromine atom, C4, H7Br. So their structural formulas are the same, the molecular formulas are also the same, but the only difference is that their arrangement of atoms. Can you look at the arrangement? It's different. And we can consider them different because there is no rotation permitted by this double bond, by the pi bond present in the double bond. Okay, the pi bond, it locks rotation. That's why they are considered as 2 separate isomers of one another. So now do you get it? What cis and trans isomers mean? Was there any question?
Yes, sir. Yes.
All right. Now remember one thing. I told you some compounds don't show cis-trans isomerism. So let me draw them out. Okay, let me draw out an example right here. This is a carbon atom attached to 2 hydrogen atoms. Carbon atom having a hydrogen atom over here and another hydrogen atom over here. So this compound will definitely not show cis-trans isomerism because this carbon is also attached to like groups and this compound is also attached to like groups. So why does this not show cis-trans isomerism? The reason is because both the isomers are going to look exactly identical. Both the isomers are going to be the same. Okay, they're not going to be different. Okay, they're going to have the same arrangement of atoms in space because the atoms are the same. Okay, they are identical. Similarly, if one side has 2 hydrogen atoms attached and the other side has a bromine and a hydrogen atom attached, so now if I were to even make a different compound, if I were to even change their positions or rotate them, so one carbon atom, this is hydrogen and this is a bromine. Okay, so one carbon atom will still have exactly identical appearance. So this would mean that if I were to pick this compound up, okay, if I were to pick this compound without breaking the double bonds, and if I were to just flip it, okay, flipping means usko घुमा दिया मैंने, ठीक है, सिर्फ इस compound को पूरा का पूरा घुमा दिया. I just flip this compound, so it will still form the same compound again. Okay, because these 2 hydrogens are the same. So these are also the same compounds. These are not different. But in case of the cis-trans isomers, even if we flip them, they'll be different. Okay, now I'll show you how. This is a hydrogen, this is a methyl group, then a hydrogen and a methyl group. Okay. Now, if I were to draw a cis isomer of this compound, it's going to look something like this: a CH3 and a CH3 over here, and a hydrogen over here. Okay. If I were to flip this compound, so what would happen? Nothing. Just both the methyl groups would go up, both the hydrogen atoms would come down, and they'll form the same cis isomer again. Okay, so it's still gonna be cis. It's not gonna form trans isomer. So that's why these 2 are exactly identical and they are different from this trans isomer. Okay, even after flipping it, it's still cis. Okay, it's still cis because the same methyl groups are on the same carbon atoms. Whereas this compound has 2 same groups across the double bond. All right, so this was a detailed explanation on cis-trans isomerism. Okay, we can even have more than 1 double bond in the same compound, and both the double bonds might be able to show cis-trans isomerism. All right, but don't worry, the examiner won't ask you to draw their isomers. Okay, actually sometimes, generally the questions in the past papers, they deal with the simpler ones. Okay, and those simpler ones can also be sometimes a bit troublesome, but all you need is a good practice of the past papers and then you'll be able to do just fine, right? Now this compound, if this carbon atom has a hydrogen and a bromine atom over here, okay, this compound also has a hydrogen atom, this compound also has a hydrogen atom, this compound also has a hydrogen atom and a bromine atom over here. So now tell me, Uzair, will both the double bonds show cis-trans isomerism, or will one of them show, or will none of them show cis-trans isomerism? Okay, so these are the two conditions, okay, pi bond presence and carbon-carbon double bonds, and let's search them out in this compound. Now, this carbon atom over here, is it double bonded? It is double bonded.
Yes.
Are both the groups or are both the atoms different? Yes, they are. They are different, okay?
Yes.
One's hydrogen, other is bromine. Now let's look at this carbon atom. It's bonded to a hydrogen atom, and what's on this carbon atom, or what's on this bond? Is it a carbon atom?
Yes.
It is a carbon atom, but we are not going to look at just this carbon atom alone, but we are rather going to look at this entire group. Okay, this entire is going to be considered as a single group. So now both the groups are different, both the atoms or groups of atoms are different, so therefore this bond will show cis-trans isomerism. Okay, and now if we look at these two double bonds, these two carbon atoms, this carbon atom over here is also bonded to one hydrogen. Okay, I'll erase out this part, okay, just to make it a bit neater. This carbon atom is bonded to a hydrogen, and what's the other group attached to it? It's the entire group over here, right? So this carbon atom also has two different groups of atoms attached to it, right? This carbon atom has passed our test and is also double bonded, so this should show cis-trans isomerism unless we look at the other carbon atom. It also has a hydrogen atom attached to it, okay? And this hydrogen atom is different from the bromine atom, right? So these directly attached atoms are different again. So this double bond will also show cis-trans isomerism. Now, do you get it?
Yes, sir.
All right. So both the double bonds will show cis-trans isomers. Okay, how to find the total number of cis-trans isomers which this compound will show? The total number of cis-trans isomers which this compound can show it can be calculated by using the formula 2 to the power of n. Okay, what does this n represent? This n actually represents the number of the carbon-carbon double bonds which are capable, okay, remember, which are only those double bonds which are capable of showing what? Of showing cis-trans geometry. Or I should rather say those compounds which have the number of carbon-carbon double bonds which satisfy both these conditions. Okay, double bond hai, so obviously it will have a pi bond, and if it has two different atoms or groups of atoms attached to it, then obviously it will show cis-trans isomers. Otherwise, it won't. So now in this case, there are two carbon-carbon double bonds capable of showing cis-trans geometry, right? So what's the value of n? The value of n in this case is, can you tell me the value of n? 2, yeah, correct. It's 2. So the number of isomers which are cis-trans are 2 to the power of 2, which is 4. So 4 cis-trans isomers are there for this compound. Examiner won't ask you to draw them, obviously, because it's going to be a bit messy. Okay, but he can ask you to draw out the cis-trans isomers of one compound, of one carbon-carbon double bond. Okay. Now, let's check how can we have 4 cis-trans isomers. Well, we have two carbon-carbon double bonds, right? What if the first carbon double bond is cis and the other is also cis? Okay, this is one combination. What if the first one is cis and the second one is trans? What if the first one is trans and the second one is cis? And what if both of them are trans? So these are the 4 possibilities or the 4 different isomers which are there that exist in this compound. Okay, cis cis, cis trans, trans cis, trans trans. So that's correct. This formula is also correct. This is how we identify the total number of cis-trans isomers which are present for a compound. Now let's take another example. All right. So how many cis trans isomers exist for this compound? First of all, tell me that. For that,
One.
uh, one is the carbon-carbon double bond that is capable of showing cis trans geometry. Yes, correct. One double bond can show cis trans isomerism. This double bond cannot show cis trans isomerism. So for the same double bond, a cis isomer will be there and a trans isomer will be there. So not one, but rather two isomers are there. Two cis trans isomers are there. Okay. So 2 to the power of 1 is 2. Two cis trans isomers are there for this compound. Okay, because this carbon atom, carbon-carbon double bond is not capable of showing cis trans because both the directly attached atoms are different, are the same, sorry. Let's take another example now. All right. So how many cis trans isomers are there for this compound? Use the same formula 2 to the power of n. Let's identify n. What's n in here? Okay, can this double bond show cis trans geometry? It cannot,
No.
because
Not.
this carbon atom has the same group, so it cannot show cis trans isomerism. What about this double bond? It has a hydrogen atom and this entire group attached. Just 1 minute. Okay, it has. Okay, it has a hydrogen atom and this entire group attached to it. All right, this entire group. So therefore, this carbon atom is okay. And what about this carbon atom? It has a hydrogen atom and this entire group attached, right? So
Yes.
both of these are
Yes.
different and both of these are different. So yes, this is possible. This one will show cis trans geometry. And what about this carbon atom? This carbon-carbon double bond over here. It has two hydrogen atoms again attached to the same
No.
terminal carbon atoms or not. So how many cis trans isomers are there? 2 to the power of 1. And 2 to the power of 1 is 2. Two cis trans isomers are there for this compound because only one carbon-carbon double bond is capable of showing cis trans geometry and the other two are not. Right? So that's it for cis trans isomers. Now the last type is optical isomerism. Okay, it's also a bit detailed. So all right, let's do the optical isomers in the next class. Instead, we'll do the cis trans isomers once again. We'll just repeat what we just did from here. Okay, cis trans isomers are actually geometrical isomers. These are the two names for the same types of isomers which are there. Okay, these are compounds. These are cis trans isomerism is possible only in compounds having a carbon-carbon double bond or a pi bond, and that pi bond actually confers a special property that is locking rotation. Okay, this pi bond has a special property due to which this compounds can show cis trans isomerism, and this pi bond actually rotates. It locks the rotation along this sigma bond axis. So the hydrogen and the methyl group which are attached over here to this compound, they'll stay up and down, and they won't be able to come down and go up relative to the other carbon atom. Whereas if that is possible and if the methyl group goes up and the hydrogen atom comes here, keeping the other side the same, then we'll have a different isomer. And a different isomer, that isomer is known as a cis isomer, because this isomer which is present over here is a trans isomer. Why is this a trans isomer? Because the same groups, same methyl groups, you can look at it with respect to the same methyl groups, or you could also look at it with respect to the same hydrogen atoms. Okay, the same groups are present across the double bond. Okay, so this forms a chair-like configuration, and this chair-like configuration is actually what's called the trans isomer. And if the same groups are present on the same side of the carbon-carbon double bond, that is either below or above the carbon-carbon double bond, they form a table-like configuration, and this table-like configuration is called a cis configuration. The two conditions which are needed to show cis-trans geometry are the pi bonds. Okay, first of all, they must have a pi bond, and secondly, they must have a carbon-carbon double bonded carbon atoms must have two different groups of atoms or atoms attached directly to them. Okay, so now carbon-carbon double bond is the first condition, because this double bond will have a pi bond which will lock rotation, and second condition is that this double bonded, each of the two double bonded carbon atoms should have two different groups of atoms directly bonded to them. Okay, in this case a hydrogen and a methyl group are directly bonded to the carbon atom, and in this other carbon atom again a hydrogen and a methyl group are attached to it, directly bonded to it, but both of them are different from one another. Okay, both of them are different from one another. Both of them are different from one another. So therefore, this compound can have both cis and trans isomers. Now, this is how the cis isomer will look like, having the same isomers on the same side, same compounds on the same atoms or groups of atoms on the same side. This is how the trans isomer will look like, having the same atoms or groups of atoms across the double bond. Okay, these two conditions are important. By the way, the examiner will ask you in the paper as well. Okay, he will ask you to give the conditions which are needed to show cis-trans geometry. And okay, so, and the last point is that they have the same molecular formula and the same structural formula. But what's the definition? The definition is that they have different arrangement of atoms in space. This is the definition of stereoisomers, which is also given for cis-trans isomers. Okay, so when you are asked to define what cis-trans isomers are, you could just give the definition of stereoisomers, and that's all. And then we did a few examples. 2 to the power of n is the formula for calculating the total number of cis-trans isomers which are there, where n represents the number of carbon-carbon double bonds which are capable of showing cis-trans geometry. All right, so that's it for cis-trans.